look through here. Functional API, that's what we're going to be covering today. Get this out of the way. Yeah, that's the start. So they refer to this wide and deep neural network, which is an interesting paper. I didn't read the paper, but he shows a new network architecture where you provide inputs you concatenate the actual inputs with the output of your network and concatenate them together and then send that to the output layer. So the only new thing is this connection here between the input and the output of the main part of your network, which gets concatenated. And remember, concatenation means just tacking on those vectors side by side. That's what concatenation does. It doesn't add them, it tacks them. It basically makes a new vector that has the length of the output from hidden 2 plus the output of hidden plus the dimension of the input layer. So that concatenation is that new vector composed of those two things. So that's the so we'll actually build that in the notebook. So let's just, and then there's a variation of it where you have part of the input that goes into the concatenation and the other part goes into the network. So, and then there's another variation where same as before, but now you have a second output. The network produces a second output that you can look at. Okay, so that's the functional API, and we're going to go back through it. Of course, I'm just sort of giving an overview of what we'll be going through. The subclassing API allows you to do, this is the key to being able to do callbacks, which we've seen that FastAI has a special, has a special feature where you can do callbacks. Well, TensorFlow has that and as well, and it looks like it's easier to use in the TensorFlow. At least to me, it looks like it's going to be easier to use callbacks from TensorFlow than from FastAI. But that's just my impression right now. Let's see. You can save models using this, and they save it to this special format called H5 format. And if you've never run into this before, it's a format for saving very large amounts of data and making them very accessible. I put a link on the Slack, just a simple link from the Library of Congress that explains a little bit. You don't have to go into it too deeply, but just read the paragraph on what H5 is. Let's see, callbacks going. And then finally, we'll get into TensorBoard and how to use TensorBoard to actually look into your model and see what's going on. So TensorBoard has features that you can visualize things that are going on, different runs of your model and so on. And we'll get into that a little bit later. Okay, so back, I'd like to go back now and just look at the notebook, starting at the functional API. Yeah, here it is. So it gives you so the functional API gives you a new way of building models that is a little bit more, you have a little bit more control when you use the functional API. We'll see that there are several different APIs. We've already looked at the sequential API. Let me back up to that, which gives you a really simple way to build a model in just one line of code like that. So here you specify that you're working in the sequential API. Then you specify each layer and the input, and that's it. And then you can run the model. So here, if you're building more complicated models, you probably want to use a different API like the functional API, which gives you a little more control. So here, you define your models separately. You define each layer separately. So you have an input layer, which basically takes the inputs and makes it into a layer, basically makes it so that you could treat it just like any other layer. Then it builds, you build your first hidden layer, your second hidden layer. And as you go through, it's the reason why it's called, the reason why it's called the functional API is because each layer operates on the previous layer as a function would. So you pass the previous layer in as an argument to the function. So the input is bunched up probably into a data bunch kind of a thing. And then you pass it to the first hidden layer. Well, you define the first hidden layer, and that works on the input. So you pass it the input. The second hidden layer has to operate on the first hidden layer, so you have to pass it the first hidden layer as an input. And then here's the concatenation piece. It needs the input and hidden too, as it takes two inputs. And so you have to supply them in a list. And this is that connection where you concatenate things together from the input and from the hidden two. You build a new input that goes into the concatenation, and then the output layer takes the concatenation layer as its argument and produces the output. So these are all the sort of the pieces that you've built up, and then you can specify the model for which you need the inputs and the outputs. So you do that, and then you can look at the model with the dot summary, and it shows you all the pieces in the model, the output shape. The output of each layer is given, the shape of its output is given, and let's see, you can verify that concatenation is what I said it does. It does what I said. It appends the vectors together. So the input had a dimension of 8, and the output of the previous layer, the previous dense layer, had a dimension of 30. So concatenation is basically going to put those vectors, it's going to tack those vectors together. So it's going to have a shape of 30 plus 8, the size of 30 plus 8. Okay, so you do the same steps as before. Basically, you put together the model from the Lego pieces, and then you compile the model. And when you compile a model, you have to give it, and this is just like in FastAI. You have to give it a loss function. You have to give it an optimizer, and then so once you compile the model, then you can fit the model. Giving it the input data, telling it how many epochs you want, and also giving it the validation data if you have it. Okay, then you can evaluate the model, and remember what evaluation does is it basically applies some kind of a metric. In this case, evaluate has a default metric, which I think is just mean squared error, but you can change that. And then the last part is to predict. Once you've completely built the model, you can then predict the model. You can predict on a new data set with the model. And so that's what this piece is. So 20 epochs, and my machine, I guess, is slow compared to, because I'm running it on my own machine rather than Colab. So it takes me roughly 100 microseconds per batch, or per epoch, I mean. Okay, and you can see that the training has started with a loss of 1.2 and driven down the loss to 0.40. With the training loss is 0.40, the validation loss is 0.3, and the validation loss is not getting better. So you can see why Jerome chose 20 epochs. Okay. And this is the one where he's changing it, so you're sending different parts of the input through. One part of the input gets concatenated with a part of the deep layer, and the other part gets sent somewhere else. The drawing in the book for that would be back up to the right page. I think it's still one back. Let's see. Yeah. So this is the drawing. So keep this in mind now. This is the drawing for the part that we're looking at now. You have the input is being split into two parts, one of which goes through these hidden layers, and the other one which gets concatenated with the output of hidden 2. So that's the architecture that we're looking at now. Remember, the previous architecture was all of the input goes into hidden 1 and all of the input goes into the concatenation. I think that's the way it was. Yeah, all of the input get. So this is sort of a modification of the original deep wide network. Okay, so keep this in mind as we go through the next piece.
Can I ask a quick question?
Sure.
So what we talked about deep. What does wide do for the model construction?
Okay, good question. So the wide is referring to that thing where you have to concatenate. So wide is making the output wider in that sense. It's concatenating, you know, you're concatenating the output of the hidden with a piece of the input, and that makes the network wider, right? I mean, it's just a colloquial way of thinking about wide. If you take off the input A, if you take off this piece, then the network is in some sense narrower than when you put this in.
Yeah, and that's my questions. What does that expanding it wider? What's a good way to think about what that's doing? So, say we have a data set with a whole bunch of features. So we know what it's doing when you go through the hidden layers and so on. But then that input A gets blended in, or at that concatenation. What does that mean exactly?
So what that does, I guess the way you can think about it is that you can tell your dog that he can ask the question next.
Sorry about
Anyway,
that. She's in
yeah,
heat.
that's okay, or she then. Yeah, so what that's doing is it's in case that input is being, well, let's go back to the first one, this diagram. Sorry, so this one. In case the input layer is being forgotten by processing through these through these layers of these deep layers of the network, you kind of refresh the memory by supplying it as an input. So in a sense, it's helping you to not forget something that you might forget if you process through these hidden layers, if that makes any sense. Does that help?
Okay, yeah.
For example, the residual networks typically just, instead of concat, will add to basically provide you the ability to do what Joseph just said. The residual connections, as they are called, would sidestep the X through the wide path and add instead of concat, which essentially achieves the goal of what Joseph is saying. And so you'll see in deep convolutional networks, the typical rest nets are those kind of connections because they have these residual connections, and the residual just says X plus whatever you're getting through hidden 2, which helps you recover the differentiated values from disappearing.
I think I get that now. Thank you. Yeah, that makes sense. So, sorry, my dog, but I think that makes clearer sense. Thank you.
Okay, so back to the notebook. So now how do you build it? How do you build this new part? Well, input shape equals 5. You define, let's see, input shape equals 6. Input. Now I'm not sure why input A and input B would be different here. You're just telling it let me.
Different pieces of the same input of size 5 and size 6, Joseph, but different pieces.
Yeah, but how do we know that it's different pieces? That's what I'm struggling with here.
That's defined, I think, when you down below in xtrain, and xtrain A and xtrain B becomes xtrain the first 4 values and then the values from 2 on to the end of the columns. Because all you're doing in the previous cell is just defining your network, which just requires a shape when you actually give it the input, then you split train into two parts, X train A and X train B, and feed them as inputs to input A and input B.
Right. So you don't have to define the inputs at this point. You're just telling, all you need to do is tell it what the shape is going to be.
Yes.
But then, okay, so let's consider that. We're not we it's kind of like we don't have to give it the actual data until we're done, until the last stage, until after we've compiled the model. So we've basically just put in a marker for an input with a shape of 5 and an input B with a shape of 6. And the hidden layers are defined as before. The concatenation is defined as before. It gets, instead of getting the whole input, it just gets input A to concatenate with hidden 2. The output is as before. And the inputs now is changed because you have to give it a list of inputs. Before we had, let's just go back up here. Here we just had one input in the previous version, but now with this modification we have to give it a list of inputs, and so that's here. I think, let's see, and okay, so now you've specified the model without having given it any data or anything. You've just told it how the model looks, and then one more step, you can give it the loss function and the optimizer. So it's all abstract. It hasn't seen any data yet. Now you define the data that you want, and X train A is apparently all the examples from 5. Well, let's see, all of the dimensions of the example up to features 0 through 4, I guess. But the second part is all of the features starting from the second feature, so they overlap. That's what's a little confusing here. And you do the same thing with the validation set. You give it the same part, the same portion. Does everybody see that this is telling you which features you want to use, right?
Someone want to get in.
Someone wants to get in. Can you try this? I've enabled the feature that anybody can let somebody in. Can you see if you can do it?
No, only you. Only you.
Oh?
Yeah.
Because I enabled that feature that anyone should be able. Anyway, I don't see anybody in the waiting room right now. Oh, there they are. Okay, you guys can't admit them. Is that true? Because before you couldn't even see them.
Yeah, even right now we can, because we see it in your screen.
I see. Okay, I tried to set the feature so that everyone can have the permission to admit new people, but I guess that didn't take. Anyway, we're stuck with the new version of Zoom, so not much you can do about that. Okay, back to this line here. You can see that the input A is everything from the feature index 5 onward. Everything up to the feature index 4. So it's 0. So it's features 0, 1, 2, 3, and 4. Does everybody see that? That's what this means. All the features up through the 4th feature. But this part says for data set B, it's giving you all the features from the 2nd feature onward. That is, only exclude features 0 and 1. So it's a little confusing because he didn't say why he's doing that, but I think you can see what that's doing, right? So are there any questions about this line?
Yeah, so now we have defined 2 training sets, but I didn't get the part, the deep and wide, where we have 2 input A and input B. So yeah, in terms of deep, we are saying we're going to take all of the features, or features just leaving 2 features?
Well, the deep only refers to the structure, to the architecture, which has the 2 hidden layers, right? And as you can see, if we go back to the book, the input B is only input B is going through that neural network. Input A is just being concatenated with the output of input B. Actually, I've gone too far. This is adding another complication. So let me go back. This is the one we're looking at right now, right?
Okay, so
Right?
input A and input B, they need to be just a duplicate copy of each other.
Yeah, you will have to because they overlap, right? So there is some overlap in input A and input B. That's what's a little bit confusing as to why they're doing that. Maybe if we looked at the particular problem we're solving, we'll understand it. But
Yeah,
for now, yeah.
Does input A and input B the same features or different?
You can see that they're not the same feature, right? They're overlapping, right? So input A, I was trying to draw attention to that before, is this part, right? Is features 0, 1, 2, 3, and 4. Does everybody see that this is what this is saying?
Yeah.
Yes. And input B is this one, which is features 2 onward, all the features starting with feature 2. So they overlap.
Yeah.
So what relates these with that 6 and 5 dimensions? What relate these?
Well, okay, so this has 5. This has 5. If you go 0, 0, 1, 2, 3, 4, that's 5 things, right?
Yeah.
So that has to have length 5. And this is 2 through the end. And I think there are 8 altogether. So it's the input number of features is, if you take the whole input, there are 8 features.
I get you.
Okay, so if you exclude features 0 and 1, that means there are 6 left.
Okay.
And that's what this does. Okay.
But he didn't explicitly say
No,
that.
he didn't. You're right. He didn't. This is a little bit. So you have to kind of really read through this and figure out what he's doing. But yeah. But I think now we're all on the same page, right? Okay. So and it would be interesting, as Srinivas said, in ResNets they actually add instead of concatenate. It would be easy to play with this and just make this add instead of concatenate and see if you get the same result or see if you get comparable results. You know, right here, instead of concatenating, one could try the experiment of just adding them and seeing if you still get a good result. Anyway, so here's the rest of it. So now we've defined the inputs, and it's only at this point that we actually let the model see the data. When we get to the fit stage, okay, we provide the training data as inputs, and the training labels and the validation data and the validation labels as inputs. So now the model sees the data and it does all of that. It takes in the data and processes it, and that's it. And then you can evaluate. Once you have the fitted model, you can then evaluate the model, apply it on a new data set, or predict on a new data set. So these 2 steps are the same as before. So back down to here, we have, at the end, we had a validation loss of 0.4. That's interesting because it actually went down to 0.3 and then it went back up to 0.4 on the 20th epoch.
Oh my God.
Yeah. Question? Lee, did you have a question?
Oh, no, sorry. I was talking to someone else.
Oh, okay. No problem. Okay, so
I still have an issue with this shape is equal to 5. I still didn't get it.
Oh, okay. Sorry, that's fine. Let's go back here. Here's the model, and this is X-train A, right? That's this piece.
Yeah.
Okay. Look at how many features we're taking in. We're taking in all the features up to 5, but not including 5, right? So that's features 0, 1, 2, 3, and 4.
Yeah.
That's 5. That's 5 features. So that's why it's of shape 5. That's why X-train A is of shape 5. And similarly, X-train B is taking all the features 2 through 8 inclusive, but not including features 2 through 7. There are 8 features, and so the indices of the features go from 0 to 7, right? And this says, start with feature 2 and go all the way through feature 7, which another way of looking at it means exclude features 0 and 1. So if there are 8 features altogether, and you exclude features 0 and 1, that leaves 6 features that are in this in Xtrain B.
Okay.
So that explains why that size is 6.
Ah, makes sense. Thanks.
Okay, great. So here we are here. Okay. Now this one is let's just go. So the next part is this.
Joseph.
Yes.
Sorry, I should have. Okay, yeah, here. So the input B here, going through these hidden layers might have been affected in some way, but input A here is not being processed in any way. So what would happen now here if they are concatenated? Because this way, the hidden ways, the input B have been processed, but the input A, the terms here have not been processed. So when we concatenate them, what would happen?
Okay, so Shamsuddin, is that you?
Yeah.
Yeah, so what do you mean by when you say that input B has been processed in some way?
So input features from input B will have to go through these layers, hidden 1 and hidden 2, right?
Yes.
And within this layer, there will be some kind of mathematical function that will transform this data, right?
Yeah, so input B goes in as of length 8, sorry, of the length 6, but it comes out as length, I think it comes out as length 30. The output of hidden 2 is of length 30.
Yeah. So
yeah.
Input A here, the features from input A, nothing like no any mathematical functions work on those. So,
right, it just has length of 5.
Yeah, so the features from input A have been transformed, but features from input A have not been transformed. So when we match them, what will happen?
All you're doing is you're just putting them end to end. So you can think of the output of hidden 2 as a vector of length 30, right?
Okay.
And the output of input A, input A is of length 5. It's those 5 features that we designated for input A, right?
Okay.
So when you concatenate them, it's just 30 plus 5. It's a vector of length 30 plus 5 or 35.
Yeah. Okay. So my question is, those vector that comes out from input A will not be the same those that comes out from input A, right?
Right. That's a good point. So they are not they're not compatible with each other in terms of length. So you can't just add them, as I was thinking before. You could if you zero padded, but you can't add them. So you're right. They're not matching in the sense that they have different sizes, but concatenation doesn't require them to match, right? If you were trying to add them, then they would have to match. Their sizes would have to match. And so if you wanted to add them, you could zero pad, you could have a little preliminary step to zero pad input A to make it the same length as in input B.
Okay.
Yeah. Okay, then let's go back. So now we're building. Sorry, I should. So now we're building a second another variation on this same architecture.
Joseph, before you go to the next variation, there's something here which is confusing, and maybe it's not used, but it's still confusing. The X text B, if you compare it to, X new B versus X text B, the dimensions don't match. And I suspect, although I haven't run the notebook, so I can't tell for sure, that X test B is not being used or something, because otherwise it shouldn't work, because if you see X test B is of dimension 6, whereas X test B is of dimension 3, because it has the same dimension as X test A.
Isn't just that 3 rows, not 3 columns, right?
Is it 3 rows? Is that the reason why?
It's
colon 3 instead of colon
comma 3.
Colon 3. Okay, right. That's the reason. Okay, so but that's important to point out that X new A and X new B are actually the 3 rows in A and 3 rows in B.
Which are already split into just 5 features and 6 features.
And 6 features. Okay.
Yeah, that's a good point. I hadn't noticed that, Srinivas. So that's a really good point. And yeah, it's so. Does everybody get that? What Raquel said? The X new A and X new B are simply the first 3 elements of these new data sets X test A and X test B that we defined up here. So it's basically giving us a little subset of examples that we can predict on.
Oh, okay. Okay, I can get, yeah, okay. Okay, cool.
Okay, so thanks for that. Let's move on to the next variation on the architecture, which is, you can see the only difference is that we're creating a new auxiliary output here, which is we take the output of the hidden, of the second hidden layer, and we process it in some way to create a new output. And they point out that a model can have more than one output. It doesn't just have to be one thing. For example, if you want to do classification, you could think of, well, the output should just be a number. I'm going to classify 35 different dog breeds, so the output should just be a number from 1 to 35. But you could also ask for the output as the probabilities. You want the probability of any image being any of the dog breeds, and so that means you would have 35 outputs. So you don't have to have just one output. And so he's showing here in this case, there's another use case for multiple outputs, and that's this extra output that has to do with regularization. Now, I must confess that I haven't carefully read through this yet to understand what this output is really doing. He doesn't really give it much in the way of explanation. So let's just sort of look at it as an abstract thing right now, that we're modifying this model to give us a new output, and we'll figure out what that new output is for. He says that the new output is for regularization. The way I think I look at it, the way I understand it, is that he's basically incorporating a hyperparameter into the model now as a tunable parameter. And you can look at outputs based on the values of that hyperparameter. I could be wrong on that. Remember, normally the hyperparameter is specified at the beginning of the model. It's a static number. It's a static setting. You don't get to change it. But apparently in this model architecture, you can tune this hyperparameter. So now it's not really a hyperparameter anymore, this regularization parameter that he's talking about.
Just to kind of add some context from my side, Joseph, you usually see that like in the inception module or like a PSP-NET architecture for segmentation that we've seen in Kaggle. And you're using a much shorter path there. So when you're like sending the loss back, when you do loss.backward, or basically propagating your stuff backwards, it's a much shorter path. If you see, it's just passing through hidden 2 and hidden 1. It's not going through that concat output. And imagine if that side is much more deeper, this is going to be a much shorter path. So it's kind of like adding on both your gradients and you're sending it back. So that's kind of the regularization there. But like when you finally run inference, like you never care about this. It's just during training time that you kind of use both of these together.
So so here he says the auxiliary output is some kind of a regularization parameter.
Right.
And okay, and it also produces an output.
So usually your output's going to be the same, right? Like if you're predicting
output,
a dog on the final output, your shorter output or your auxiliary output is also going to be predicting the dog. But then imagine like it's just going to be using hidden 1, hidden 2 to make that prediction. It's not going to touch concat or anything down that chain.
Right. So in some sense, it's not seeing input A, and so it's going to tune this parameter, but it might get the wrong value because in the full network you are using input A. So I'm not
that's why when the very next part, I think you see that you kind of weight those, right? You're weighting this aux will be as 0.1 and the final output is like 0.9. So
oh, okay.
Still using both the losses to backpropagate But like you mentioned, like aux is looking at a very smaller part of the network, so that's why you weight it lesser. Versus the final combined thing is what you want to weigh more. So that's where you kind of blend those two together.
Okay, right. So then in a later step, I remember he actually weights these two, and he gives this one a smaller weight and this one a bigger weight.
Right.
Again, that's just empirical. You just say, oh, I think this should be 0.9 and this should be 0.1. I guess those are also hyperparameters that you can play with.
Of the losses, right? And there I had a question. So if you define this structure, but then you want to ignore the aux output and the loss, and you just want to train based on the full connections on the left, is there a way without redefining the network to just zero the weight to aux, and it would completely go and put a weight of 1 on the output, and then it would work?
That's right. That's what you would do, right? You would actually do exactly what you said, and then it would not take into account the result of this aux output.
So you need not change the model, but just change the weights, and it should work, right?
I think it's basically aux output is just an output, right? So even if it predicts it, and like at inference, you don't care about it, right? So when
right. No, but I was saying you could retain the network, and I mean, you can define this network and then just train on the left-hand side if you wished, by making the weight of that 0.
Yes. Yes. Yeah, so you could try, in other words, that would give you the ability to see if that made any difference in the result. But I think what you said is that, see, I think what Srinivas is getting at is that these blue output levels, they always involve a loss function. So, and when you train, you're forcing, if you specified a loss function here and a loss function here, you're forcing the training to take into account the loss function from both of these. So it's not that this doesn't matter. If you put it in, and if the weight is greater than 0, then it will be, the network will train on it, and so it will matter to the output.
Right. I think I didn't mention that clearly. Like during training, you're right, it will take into account. But I'm saying during inference, you never care about the aux output. At inference stage, you only want to care about.
Yeah, because you already have your model.
Right.
Your model's
so at that
built.
point of time, even though it'll return back 2 things, you just neglect the aux output. That's where, but yeah, absolutely. While training, you very much add that in so that it'll kind of send in more back during your backward process. So it very much affects your training process.
Yeah. So that's the thing. So yeah, excellent point. So keep in mind that these blue squares here, the output layers always involve loss functions. And so once you give them loss functions, then that becomes part of the training. Okay, and so whatever happens here affects whatever happens here. Whatever the output is actually affected, except if you do what Srinivas said, which is to say, give this a weight, give the right-hand branch of the output a weight of 0, and then it's as if this isn't even there. So with one model architecture, as Srinivas said, you could actually use it 2 ways. You could use it to reproduce the previous architecture that we had before by just setting the weight for the right-hand branch equal to 0, or by not setting that, by having the weight greater than 0, then you activate this part of the network. Yeah. Any questions there so far? Okay.
Joseph, to your point, I think Rickle's point is worth emphasizing that, I was you could get the original network by making it a 0. The difference is when you don't make it 0, then the training of the overall network changes. And if you make it 0, then the training is also identical to when you make the aux output loss weight 0, then training this network is identical to training the previous network. If you have any weight other than 0, then as Raquel was saying, when you train this network, it will give different outputs than it would with the previous network.
Yes. Are there any questions about that so far?
Yeah, so as far as like what do you mean by giving a weight to this auxiliary output? Isn't that weights are hidden, which is learned by the network itself? Like,
yeah, that's a good point, Dinesh. It's kind of like a an sort of an how do you call it? An overloaded use of the word weights. Yeah, because this involved these layers involve weights, and now we're talking about weights again, but really we're talking about somehow we're taking a linear combination of the loss functions, because that's what it does when you have two different outputs or many different outputs. What the training does is it adds together the loss functions from these two with certain weights. So you could say I want 75% of this loss function plus I want the final loss function to be 75% of this loss function plus 25% of this loss function.
okay.
And in that sense, we're talking about weights. It's kind of an overloaded use of the word weights.
Okay, so it's more of like how you want to use the architecture. You have the flexibility, both either you can use only the left part, or you can use the mix of left and the right, both of them based on your data set or requirement as such.
Yes, that's right. So let me see if I can get a pen here. So yeah, so as Srinivas and Raquel pointed out, by giving a weight of 0 here, so we can so the actual loss function, this is kind of implicit. The actual loss function that your training is going to use is going to be loss 1 is going to be a combination of loss 1. So I should write this as a linear combination, some constant A times loss 1 plus a constant B times loss 2. And those constants A and B are these weights that we're talking about, right? So, in Jeroen's example, A is 0.9 and B is 0.1. The point is that the overall loss function becomes a linear combination of the loss functions from all the output layers. In this case, there are only 2 output layers.
Okay.
Does that make sense to everybody? So the actual, yeah.
Is this a loss function on both the blue boxes need to be same, or you could use?
Yeah, he says that they're the same, but I guess you could use. I suppose you could use different ones if you wanted to. If you had some reason. Yeah, it could, because of the flexibility of Keras allows you to choose, a loss function at any stage whenever you're specifying the model. So.
But more often than not, you're trying to predict the same thing on both the branches. It's just that one is shorter than the other branch. So, I mean, I've usually seen using the same loss because you're either doing classification on both of them or regression on both of them. So, but there is no reason why you can't use 2 different loss.
Right. In a general case, I haven't seen, and I don't have experience with this, but I know that when people build, models that do more than one thing. For example, for natural language processing, people are now starting to build models that do, text summarization, translation, text prediction, many different NLP tasks all at the same time. And how do you think they do that? Well, they do it this way. Each task has its own output, and each output has its own loss function. And in that case, the loss functions might be different. So the model becomes really complicated because you have all these extra weights to worry about, extra weights to specify these A's and B's. You can imagine there could be, I think there's a model called T5, Transformer 5, which optimizes 5 tasks at the same time. And I don't remember exactly what those tasks are, but you know, you can probably find that online.
Even object detection for that matter, right? You want to specify whether there's a dog or a cat, and then you want x, y, width, height to draw the box around it. So there also you're doing classification plus regression. So you're doing 2 different tasks at the same time. The difference with that versus this aux losses, there everything is getting predicted at the output layer. You don't have this concept of the aux loss. Aux loss is usually somewhere midway in the branch.
Mm-hmm.
Whereas in the when you're like T5 or the other example of object detection, usually everything is predicted right at the final output layer. This is why this, I think Jerome makes the point that this is helpful for regularization and helps in training, is because like halfway between there, you know that the gradients have flown much more than what it would have flown to the final output layer. So that's why you're helping in the training process by kind of feeding it back from here also.
So when you do this task of classification plus localization, which he mentions, you know, where object detection, which he mentions, so you could have different loss functions for those. Like classification, you would want the you know, the cross entropy loss, and for object detection, you would probably want the squares loss.
Right, regression.
I got to unmute somebody here. There we go. Yeah. So so TensorFlow gives you that. So I'm not sure how they do it in the models you're talking about, if they build that in into the details that you don't see. But here you can actually control that and have different. You know, you could have the auxiliary output be the mean squared error loss for the you know, for the object detection task, and then the other part could be the cross entropy loss for the classification task. And then you still have to worry about what weights to supply, which one is going to be the most important, or whatever.
Isn't Raquel's point that the difference I take away from what Raquel is saying is, see, in the case that you explained of the T5 and also Raquel's example of the output of the object detection case, the difference is subtle, but it's the fact that, think of it, and again, even if I use the term head, think of the object detection in the T5 examples as kind of sticking to the output layer. So it's at the same, for lack of a better word, depth output at the end. Whereas typically the aux outputs are taken somewhere in the middle of a very deep. And even though they are also head and they give an output as well, where they structurally sit in the network is more, quote, for lack of a better word, middle or less number of layers, versus when you combine outputs like providing multiple outputs for object detection or multiple outputs for the T5, you are putting them at the end of the deep part in all cases. Now, in both cases, the losses flow back. When I say both, what I mean is the both sets, when you put the heads at the end of the deep or when you put the aux in the middle of a structural thing. But Michael's point, I thought, was that the reason you put this aux kind of thing in the middle of the structural is to give you better control over the regularization, or the fact that you have shorter path to get back. In both cases, you obviously end up combining the loss, but that's what I take away. Is that?
Yeah, that's what my main thing is. Yep.
Okay.
Yeah, understood. So yeah, I mean, I was just emphasizing the point that that a model can have multiple outputs and can be optimized on multiple different loss functions, one for each output, right? I mean,
yeah.
And you would have, and if you had a model like we were talking about before, the classification plus detection task, each of those tasks has a different specialized loss function that's best for it. And so TensorFlow gives you the flexibility to find different loss functions for each of the pieces. But the architecture, as you point out, Srinivas, the architecture for something like T5 would be more like this, where at the end you have multiple output layers, you know, and they're all at the same level in the network. Whereas, as Rekul is saying, that the you know, this auxiliary output is architecturally different because it's buried inside. It's an intermediate result, and it allows more control since it doesn't have to go through as much computation, so the regularization can flow back more easily.
Yep.
That's what Rekul's point is, right?
Yes.
Okay, right. So yeah, so both of these points you should take away from this, that you can have multiple output layers, A, and B, those output layers don't have to come from the same level in the network. They can come from different levels in the network if that's to your advantage. Okay. Anything else? Okay, now let me clear all my drawings. Okay, all right, so now let's, oh, I gotta get back the cursor. There we go. So now let's go back to the, and build this one. So you can see architecturally, it looks similar to the one before. The input parts look the same. The hidden part and the concat part looks the same. But now we have to build two outputs. That's the only difference. So we build, and we can actually name them. So for reference later on to help us keep track of them. So the output is a dense layer on top of the concat, and the auxiliary output is a dense layer on top of hidden 2. So hopefully that makes sense to everybody architecturally. Let me go back to the book. Right, so the first output is coming out of is a dense layer that operates on the concatenation of these two vectors, the input A plus the hidden 2, right? That gives us our first output, and the auxiliary output is a dense layer on top of hidden 2. So with that sort of picture in mind, let's go back to the notebook and see. That's what these lines are telling us. The only lines that are different are these lines building our outputs. And then in the model specification, the third line that's different is we have to give it a list of outputs now because we have more than one output. Okay, so that's that. And I just wanted to see that the loss at the end looks like it's similar, about 0.4 after 20 epochs. And let's see, total loss, main loss, auxiliary loss. So out of the evaluation part, you can actually get the total loss, which would be the weighted two losses. Now, and this is the main loss, and this is the auxiliary loss, because as we mentioned, each of those blue boxes has its own corresponding loss function. So let's just see how we put the weights in. So that comes in here. We gave it weights of 0.9 and 0.1 out for output and auxiliary output. So if we wanted to use this to implement the previous model, then we would do as Srinivas said and put this weight equal to 0, so that it wouldn't consider the auxiliary loss at all, and this weight would be 1. And if we gave it no loss weights, then it would assume that the weights are to be equal. Everybody see that? So so this is how we actually have that flexibility to tell it what to do about to tell it how to incorporate the two outputs into the model. And other than that, this step goes the same, looks the same as before. And so, okay, next we do the subclassing API. And here
one difference, right, Joseph, in the previous case, that you have to provide two outputs to check against to create the backprop. So it's Y valid, whereas earlier we did only one Y valid when there weren't two outputs. If you go up a little bit.
Yeah, right. So we have outputs here, and so you're right. This step is also different. It's not the same as before. You have to give it, let's see. No, actually, validation data is the same, right? This step is the same. X validate. Here's where we, here's where we told it that we wanted it to use two outputs, right?
Right, but then didn't we? I thought even in the text he says you have to provide.
Yeah, we're providing Y train, Y train, Y valid, Y valid.
Yeah.
In cell number 400, Joseph, you've passed in X train A, X train B, and then you pass Y train, Y train. So you're predicting the same output on both those branches.
I see. Right. That's a good point. Right. So yeah.
And if you compare it to the previous, you would see a single Y train because there's only one output. You're splitting the input, but in the previous case, you only have one output. So you just have Y train or Y valid single values. You have multiple input values. In this case, you have multiple inputs, multiple outputs.
Right. So that comes in both in the training and the validation. You have to give
Correct.
it both outputs.
Yes.
And that's because in this case, we're training both of those heads, so to speak. Both of those outputs are being trained against the same labels.
Yeah.
It doesn't have to be that way. You could have different labels for the different outputs in another architecture.
Right. When you talked about T5 and others, then you would obviously provide different outputs to check against, right? Because the nature of the object detection thing Rekil was talking about, then the outputs would be different.
Yep. Good point. Yeah. So that's a good point to keep in mind. Then you have to specify the outputs that you're training, the labels that you're training against for both of the output heads. Okay, so the next part is the subclassing API. And here he shows that this is like even a more flexible way to create a model. And it's for, you may never need to use this, or you may always want to use this depending on your personality type. I mean, if you want to have really fine control over the model that you build, then you might want to use the subclassing API. And so here you can build a class that subclasses the model class. That's why it's called the subclassing API. You build a model that is you're actually building a class that has the Keras model as its subclass. So it inherits from that. So you give it the pieces, the hidden layers, you specify them. You specify the outputs, the two outputs that we talked about before. And this one tells you the dimension of that output, the one here. It specifies the dimension of the output. Because in our case, it's just a vector it's just a number. And then you have a call method that that computes the outputs, that actually propagates everything through the model and computes the outputs. So you tell it that you have inputs, and again, we leave the specification of the inputs till the end. You don't have to specify them inside of this class. So then you build you apply your hidden layer that you built here when you initialized. You apply that to hidden B. You apply hidden 2 on top of that output. And the concatenation is concatenate operating on hidden A, on input A and hidden 2. Those are the two outputs that you wanted to concatenate. And then you construct the main output from concatenate and the auxiliary output from the hidden 2. And then you return both of your outputs. So this method is clear what it does. It basically implements it basically implements the network that you've specified. Or actually, it actually helps you specify the network. It implements the layers. It puts together the layers that you specified here into a coherently structured network, and then computes the outputs.
For those who have played with PyTorch, is it question? This very similar to just inheriting from nl.module in PyTorch and doing the same thing with forward, right? So is there any other major difference rather than subtle differences of how you specify that similar, or anybody who has played with both know any significant things that are different? Because it seems practically identical to PyTorch inheriting from nn.module and then defining forward and initializing.
Yeah, I don't have an answer to that.
Because it seems very almost identical to the PyTorch way of just inheriting from nn.module inside of like wide and deep model, and then instead of call defining forward.
But it seems like, I think that he's going to show that inside of call you can have callbacks. You can have callbacks interspersed in there.
Yeah, I think you could do that in PyTorch too, Joseph.
But not in forward. I mean, not in the method forward doesn't have that flexibility.
Yeah, here also, I don't think you'll put it in the call, right?
Yeah.
Well, let's see. Okay, well, let's just go on and see how this
works.
Yeah,
one other question on this part. Maybe people have tried. If not, I'll try. But just a quick question. He specifies the 30 in the. If you go up just a little bit, he specifies the 30 in the. Not here. Just if you scroll up a bit to, yeah, right there. He says units equals 30. You don't have to do that, right? You can specify individual things within the dens and make them different.
I think so. I mean, I think you could maybe do units 1 equals 30 and units 2 equals 40 or something, like if you wanted to have different units to use here.
Right.
So yeah, I think you could specify different values. You could put in you could put in a list or something maybe, and if you didn't want to constrict yourself to having only units, only 30 vectors of length 30. Yeah.
Okay, we'll play with it. Thanks.
Yeah. And let's see. You supplied an activation function here, and he said, oh yeah. So you specify the activation function here, and then you implement it here. And again, in a more complex network, you might have 2 different activation functions, or even 3 different activation functions. As we've seen, the LSTM model uses sigmoid, tanh, and ReLU. So you might have to define several different activation functions here, or a list of activation functions that you can then pull from when you instantiate these layers, or when you define these layers. Sorry. Yeah. So okay. So now we've used this class to build the model. Well, we've used this class to specify the model. Here's where we actually build the model. We're basically just calling an instance of this class. And then we compile the model as we've done before by giving it a loss functions and an optimizer. And here the difference is we have to give it not only a loss function, but we have to give it the weights of the loss function. I think we already saw that in the previous version. So normally when you compile a model, you need a loss function and you need optimizers, but in case you have more than one outputs, you have to specify what the weights should be, or you don't have to specify. If you didn't specify the weight, it would just assume that you wanted equal weights. But if you really want the weights to be different, you have to specify them in this parameter here. Okay, and then as before, we fit the model, and here we're giving it 2 inputs and 2 outputs, as Srinivas and Rekil pointed out, and again 2 inputs and 2 outputs here. And then when we evaluate the model, we can get at the individual pieces of the loss function, the auxiliary loss, the main loss, and the total loss. You might argue that you don't need the total loss, because if you have the weights, you can actually calculate it by just adding them together with their weighted. You can do it a weighted average, but it is built in that you can get all of the loss functions out, the total loss function and all the components from the evaluate function. And then finally, also the predict function also allows you to get both outputs out, because you have two models in, so you're allowed to get two predictions out. And so that's what this last line is doing, is it's taking that new data set. Remember, we defined it as the first 3 lines of the test set, the first 3 elements, the first 3 entries in the test set, and now we're predicting on those. So let's see, at the end we should see those predictions come out. Let's see, ypred aux. We could get them, and it's not going to print them out. But what it did tell us is that the loss function is 0.7145, the output 1 loss is 0.5205, and the output 2 loss is 1.17. So 1.176. So if you added these together, if you took a weighted average of these with 0.9 times that plus 0.1 times that, you would get this. You would get the total loss function. Okay. So
I don't know if I missed that, Joseph, but does it say in the book that if you don't specify the loss weights, they are halved? Like, is it equal? I don't know if I saw that in the book or I missed it, so I just wanted to double check.
I think I saw that. I mean, because okay. if you didn't do that, I mean, if I were building this code, that's what I would do. You wouldn't want the code to blow up if you didn't specify losses or to throw you out. But you can check it. I believe he did say that in there somewhere. Okay, so then the next part, any other questions before we go on? Okay, so the next part, we're going to just basically, we're going to try to save the model. Well, we can somehow, we're not actually saving it in a file, we're just storing it, okay, for later use. Oh, he actually did that already. I don't know why he did that again. Oh, maybe now because, oh yeah, because now you've added all of these extra functions, you've compiled it, you've fit it, so now you have to save it again because this command doesn't do the same thing as this command. I mean, this command only saves the model up to where you built it. You know, you haven't even given it an input yet, right? So this model knows all of this stuff, all the stuff that went before to specify the model. But here we've actually instantiated, we've compiled the model and we've actually run the model and so on. So this time when you save the model in this, it's going to include all of that. It's going to have all the input data. It's going to have all of the predictions and all of that are going to be accessible. So does everybody see why these two commands, although they look the same, they're not? Scikit-learn works this way too. As you run the methods of the model, it accumulates new data objects that you can access. And here those objects are, you know, we can get at the, we have this evaluate method that we can run. At this point, you couldn't run an evaluate method because you didn't have, you haven't gotten that far in specifying the model. You haven't fitted the model yet. But once you've done that, once you've run this step and this step and this step, now when you save that model, you save the model in this variable. Now you have access to all of the objects that were accumulated as we processed the data and ran the model and evaluated and predicted.
Most importantly, the model's weights have been trained in through the fit, right? So you have the model with its weights, which can predict.
Right.
Isn't the dot compile and dot fit both methods on models? I was it'll already be tied with model.
Sorry, you were breaking up. Can you?
Sorry, I was saying that the dot compile, the dot fit, they're all methods on model, right?
Yes.
They are tied to model already. So this may be a noob question in terms of object-oriented programming. So I still don't see why 404, line 404 is required.
Because, okay, as you said, it already has these methods attached to it, but these methods will be none up to this point because you haven't done
run
anything
them,
with
right,
it.
Raquel? You haven't executed them.
If you
You
try
have
to
the
get,
model.
if you run up to here and then you ask for model.fit, it will say none because, or something like that, because it hasn't done it yet.
Right.
So at this point, all it has in it is the structure of the model.
Right. So
as you've defined it.
I agree you need to do the model.compile, model.fit. What I'm saying is, why do you need to do the one after that?
Oh, because now when you save this thing, it now includes all of these objects that it's now filled in all of these things. It has the compiled model, it has the fitted model, which, as Srinivas pointed out, has produced all of the weights for us. So here, if you stop at this point without having done all of this stuff, of course you can't access the weights. There are no values in the weights. But once you've done all of this, once you've compiled the model, fit the model, predicted and so on, evaluated the model, now you can access all of the outputs of those procedures through the model that gets constructed when you say model equals wide and deep 30 activation equals ReLU now has all of those objects in it, if that makes sense.
The state of the model has changed, right? Because
yes,
the state
that's the
values within the model have been updated to reflect the running of the methods fit and compile, which you did not by executing model equal wide and deep model previously. So in an object-oriented way, the state of the model between the two statements is different, and the state includes and I was just focusing on the weights, and the weights are the most important thing for inference and stuff, and you would have nothing before you ran those, and then after you have run it, you can just use the model.
So 404 is not required, right?
Yes, because well, no, and if you need it, you could still access it this way, right?
No, I'm saying if you still do model.fit or model.predict, it would still work.
Yes, so if your point is that if you, after you have run this fit and compile, he's using model.predict, and so he's able to predict. So you don't have to, again do wide and deep before you predict, for example.
Exactly.
I now see your point, Raquel. I now see your point. So yeah, because all of this was done in line, and every time you do one of these methods, every time you run one of these methods, you change the state of model. So you're right. You're right. So you don't really need to do this again. Yeah. Thank you. So anyway, the point is that once you run the model, you can now access the important pieces of it for future reference if you need. And there's lots of things that allow you to. There's a lot of things you can access, and that's what you can get at by looking at the DIR of the model. There's all of these pieces. You don't really need to know all this stuff now, but they're there in case you need them. So here's, for example, the loss function, the total loss function, and so on. Okay, and then he points out, he takes you through this save method, and it's kind of disappointing that you can't use it when you've built a model using the subclassing API. So that's a little bit disappointing. So he shows you how to do it by building a model freshly, and then building a model freshly using the Sequential API, running the model, and so on. And then you can run this. It has a method called save. It allows you to name the model and save it. And here, it's showing that it's saving it into an H5 format, which I talked about, which is an efficient way to save large files. You can think of it that way. And then once you've saved it, you can then load it. So so that you can finish doing some large calculation and save it away and then go somewhere and then come back and load it saves it in a file. You can come back later and save and load it in and take up where you left off. So that's a nice feature.
Joseph, have you tried pickling, and does it not work and only H5 works for?
I have not tried. I've not tried, and maybe there's a pickling option, but I haven't explored that yet.
That'd be interesting to try, because most FastAI models, PyTorch models seem to be able to, unless you do Lambda functions, you can pickle and load most of them unless you do something inside them that prevents it, I think, if I recall correctly.
Yeah, I remember that. And I don't know what the situation is here, but it would be interesting to explore that. And then he mentions that if you've built a model using the subclassing API, you can't use the save function on the whole model, but you can still save the weights and pieces of the model. I think he said, what did he say? You could save the weights and the losses or something like that. And so here's how you would do that. You would use the save weights method, and I think that method works on subclassing on models that were built with the subclassing API. And I'm not sure what the CKPT is, but it must be some kind of checkpoint. Okay, so that's just a label for you.
As opposed to a .h5 file.
Okay. Okay, checkpoint file. Yeah. So this is how you would proceed if you if you built the model with the subclassing API and you wanted to save it and access it. Okay, and then finally, well, I guess we're out of time, so it's 10 after, and I've already kept you 10. But so we'll just start with the callbacks next time. I think that's probably one of the most important pieces. And then the TensorBoard. I know that Mosh was eager to talk about TensorBoard, so we'll have to combine those into the last lesson, and we'll make sure and give it proper attention to TensorBoard so that we can answer Mosh's questions.
I feel special. Thank you.
Yeah, you are special, Mosh. Okay. All right. So everyone, enjoy the rest of your weekend. If you're in a time zone where you have the rest of the weekend. Otherwise, enjoy your week, and we'll see you on Wednesday.
Thank you, Joseph.
Many thanks, Joseph, and everyone.